All right, welcome back everyone to Physics 4 on catastrophe theory. So catastrophe theory is an application of singularity theory and differential topology to give a new mathematical perspective on thermodynamics. Obviously, there's other areas of mathematics that are relevant to thermodynamics, calculus, differential geometry, but catastrophe theory sort of focuses on a different set of concerns in thermodynamics to some of those other mathematical connections. So the main reason to bring it up in this context is that we've heard so far this week about various analogies between thermodynamics and learning. They've basically all gone through statistical physics and the Boltzmann distribution, basically, right? And the key point of connection was that the Boltzmann distribution with a microscopic stochastic Hamiltonian looks a lot like the Bayesian posterior. So if you formulate everything in terms of such integrals and their derivatives, then you get pretty direct connections. However, there are big differences between what a physicist usually means by thermodynamics in, say, an undergraduate course, where you're talking about fluids and heat engines, and the context we find ourselves in learning theory. For example, we don't obviously have a volume or a pressure. We have a thing we call a temperature, and we've discussed sort of how that relates in some sense to the number of samples. Now, the reason why, okay, so you could come to this dictionary and you could think to yourself, okay, I'm going to sit down and think really hard about what volume is in learning. And well, you might actually derive some useful intuition from that. But that's not actually the exercise I'm suggesting you do at this point, right? That's not the purpose of this dictionary. Now, the reason for that is that volume and the other macroscopic quantities that you want to focus on in thermodynamics are ultimately functions of the microscopic symmetries that exist in that domain of physics, right? Physical systems sit out in the world. The world has a certain number of dimensions. It has momentum. It has angular momentum to do with fundamental symmetries of the physical laws. And through the averaging process that Jesse was describing, those microscopic symmetries give rise to macroscopic invariance over short periods of time and averaged over space. If you switch to a different universe with different physical laws, like the inside of a learning machine, you have different microscopic symmetries and different quantities you want to build your theory around. And we don't probably know all the relevant quantities. Okay, so I first of all think that this thermodynamic analogy is one of the main ingredients going forward to applying SLT. Secondly, we don't have a fully fleshed out sort of view on what that thermodynamics is. Third, just like cracking open a thermodynamics textbook and being like, letter V, what does that mean in learning theory, is not the way to go. Okay, so we have to be more sophisticated about it. And I want to give you the beginning of a mathematical framework for being more sophisticated about it. And hopefully by the end of today, you've got at least a little bit of a way into that. Okay. We've also talked quite a bit about phases as local minima of a free energy and also as regions of parameter space in statistical learning theory. The relation between those two things was that, well, a local minima is a certain kind of critical point. We're using critical point and singularity basically interchangeably. I think I should comment on that. So a critical point of a function just means a point where all its derivatives vanish. In algebraic geometry, we would say a singularity of a function is where all the derivatives vanish and the function is zero. But who cares, right? Because you can always just shift the value of the function by adding a number. So really there's no essential, unless you're actually in a situation where you're comparing zeros and you care about them versus other critical points, critical point and singularity can be used sort of interchangeably. If you like, you could read critical point as singularity of a different level set. Okay, so mostly I'll say critical point in this lecture, but yeah, just read singularity if you want to connect it to the rest. So the relation between these two was, as we've explained, that regions of parameter space, their free energy is dominated by singularities of the negative log likelihood. And similarly, phases in physics are dominated by local minima of the free energy. But you would be forgiven for thinking so far that we haven't really given a very precise mathematical definition of a phase or a phase transition. That's because it's like area, or like some fundamental mathematical notion that has like 4 definitions in slightly different domains, right? This is a very, very deep notion, phase transition. There is no single definition of what this thing is. Don't expect to find one. It's like a quasi-physical notion that has manifestations in many different kind of formalisms. So I'll give one very precise definition today of both things, but you also shouldn't think that there should be like some grand unified definition which all of these fit into. I think that's a bit of a mathematician's curse to look for such things. Okay, to go beyond inspiring analogies, we need more abstract mathematical formulation. I said that already. So here's the high-level dictionary, which I'll explain over the course of the lecture. We sort of understand, or we've said, that phases and critical points correspond to each other in some sense. What I'll explain today is that the phase portrait is related to what we would call in singularity theory the unfolding of a singularity, which you could think of as the deformation, like all the possible ways of pulling apart a singularity in the sense of something nearby in a relevant space of functions. That phase portrait, and on the left you think about the phase portrait of, say, a fluid, like Jesse was showing the other day, with phases and coexistence lines and a triple point and a critical point in the case of water. Well, that has some structure in it, like the lines that divide the phases, the coexistence curves. That phase structure over on the right-hand side corresponds to a stratification of the unfolding. Stratification just means a series of larger and larger subsets which together kind of define the relevant structure. And I'll explain this not in general, won't go into stratifications, but in the case of the cusp catastrophe, or A3 singularity, which is the thing on the right-hand side that corresponds to the simple phase diagram of a fluid that Jesse was presenting, I will talk about. I plan to actually present this. I think I won't have time. So the van der Waals equation is basically can be derived from the right-hand side with some asterisks. Okay, the reference is Gilmore's book, Catastrophe Theory for Scientists and Engineers. There's quite a few books on catastrophe theory. It has a bit of a history, so really many of the ideas go back to Poincaré, which was implicit in Jesse's lecture yesterday. So this idea that there should be a deep link between singularities, which are local phenomena, and global topology sounds like the kind of thing Poincaré might be into, and indeed he was. So some of the most fundamental theorems in that connection are due to Poincaré, the Poincaré-Bendixson theorem, for example. So really, René Thom picked up this idea again and pushed it quite far mathematically in the context of differential topology, proved some beautiful theorems, and then wrote a very heartfelt book explaining all the things you might be able to do with this beautiful theory. Then some others kind of took this and maybe applied it in a way that was a bit too speculative, and there was a backlash. So you may or may not be aware, but catastrophe theory has a bit of like a bad smell to it in some quarters. I think that's kind of just disappeared into the past largely. So now catastrophe theory gets used all over the place, and it doesn't really have this reputation anymore, it seems to me. Anyway, that's sort of irrelevant from our point of view. The math is solid. So for us, physics today is going to be all about a potential. So there are many more dynamical systems that are not governed by a potential, but under some conditions locally, even ones that aren't governed by a potential globally are governed by one, and it's sort of a reasonable class of systems to consider. And certainly in the case of a system trained by gradient descent, it's kind of the relevant bucket of physical systems. So we're going to consider a potential, which is a smooth function V. There are two kinds of variables. I don't write r to the n plus k because I want you to think about them differently. So x, that stands for x1 through xn. Those are called state variables. You think of those as the configurations of the system, like positions and momenta of particles in a box. The other variables, C, there's K of those, are called control variables. And you think of those as being like temperature and pressure. Okay, so that's where the handles are, right? You can tweak the values of C. You don't get to touch the values of X directly. Physics is controlling those. It does something with those variables governed by this potential. The system, which is associated to a potential, is defined by this differential equation, or this family of differential equations. So for I 1 through n, dxi dt is the negative xi partial derivative of vxc. Okay, so that just says that the trajectory of the particle with coordinates x is governed by negative the gradient of v, but only in the x directions, right? As I said, so think of the c's as like the constants. If you were to write down a potential, like Jesse wrote down the Hamiltonian for the Ising model, it had a h in it, right? H is a control variable. It sits in the Hamiltonian and therefore sits in the time evolution equation for the state. But you think of that as like sort of fixed, and then you run the dynamical system and see where it ends up. And then that's some state. And if you were to tweak that magnetization, we sort of actually talked about that, right? In the context of the phase transitions. So yeah, that's the kind of quantity you want to have in mind for C. And what we think of is for each value of the control parameters, we think about all the solution trajectories, right? So all the solutions to this differential equation with varying initial conditions, and have in your mind all those trajectories as like a single object. And then as you vary C, see in your mind as those trajectories shift. Now, for most variations in the control parameter, the trajectories just kind of bend a little bit, right? Like you're changing some like very slight change in the parameters that govern the force that's, affecting the system, for example. And that it only changes the solutions in some sort of quantitative way. But there are some particular values of the control parameters such that if you vary the control parameter through those critical points, I don't really want to call them critical points, because in a moment I'm going to define critical points to be in the x coordinates. So delete points on that slide, okay? So at some critical values of the control parameter, those solution trajectories, all of them together in your mind, they don't undergo a very slight change with the change in C that goes through C0. They change in a discontinuous way. Okay, Jesse talked about some examples. Okay, so that's the sort of overall structure of the relationship between state variables and control variables. So here's an example. In fact, we've seen this already. The name is new, the cusp catastrophe. We haven't said what a cusp is, and I haven't said what a catastrophe is, but I will in a moment. So this is a potential with one state variable x and two control variables a, b. And the corresponding gradient system is just x prime is minus x cubed plus ax plus b. Okay, some more names for this are A3 unfolding, A3 catastrophe, or cusp catastrophe. As Jesse said, if something has many names, probably it is important. This is by far the family of potentials, or it's a singularity, which appears most commonly in applications in the world, for reasons that I'll explain actually. So it's like we have some mathematical reason for understanding why this comes up all over the place. Okay, so you need a few like mental models for this picture that I told you to have in your head of all possible trajectories. There's several ways of thinking about that more precisely, and I want to teach you a couple. One is just plot the things and have a look. Okay, so this is not the trajectories, obviously, this is the potential itself. So for different values of A and B. I mean, the reason it's hard to visualize, obviously, is because you have to visualize a two-dimensional space, and at every point of that two-dimensional space, a curve, which is the graph, well, I mean this graph, a graph of V as a function of X. The X axis here is X, it's unlabeled, sorry. The vertical axis is V. So when you fix A and B, you get this curve. When A and B are 0, it's just 1/4 x to the 4. It's this flat basin potential we've seen in Liam's talk, probably also in Jesse's. Okay, but if I take just some other values, let me take A equals 0, B equals 4. I see here that now it doesn't look as flat. There's one critical point down there and like something happening over there perhaps, but just one critical point on the left. If instead I take B equals -4, there's one local minimum on the right. A equals 32, B equals 0. That's not flat anymore. That's just a parabola. This is very interesting. So A equals -8, B equals 0. Now I have 2 local minima and 1 local maxima. This is also interesting, right? You see over here, there's 2 critical points, one of them around 2 and the other one a bit less than -2. The one on the left is a local minima, the one on the right is a saddle. Yeah. Okay, so that's one way of looking at them. You just pick various values of A and B and have a look at V. Now the differential equation is saying x prime equals minus d dxv, right? So clearly then, if you're over here, you're going to take minus d dx of v, which is going to send you backwards, right? So here you think about the particle kind of rolling around in this flat bottomed well. This is a simple harmonic oscillator, and these are doing whatever they do. But coming back to a point Jesse made in his talk, where actually, I mean, it's infinite. To care about this graph is to actually miss the point, because most of the behavior is governed just by knowing this diagram, right? I just need to know that this is actually a constant solution if it starts at 0. I said it was rolling around. I mean, I'm injecting some kind of finite step size or randomness in my mind when I say that, so I apologize. At this level, that's not what's happening. This is a constant solution at the origin. If you start a bit to the right, then you're going to move to the left and asymptotically approach that. Similarly, on the left, you'll approach it to the right. Okay, so the other diagrams on the first row just correspond to the different location of that minima, but the dynamics is basically qualitatively the same. Okay, and that's what I was saying earlier, right? You have this picture of solutions in your head, you're varying the control parameters, which in this case are A and B. The nature of the solutions is changing. The change from here to here to here is not changing the qualitative nature of the set of solutions. Okay. But, okay, here, well, sorry, that's mistaken. There is a difference because this is very flat. So you're meant to look at the size of the arrows here. So these are small arrows, right? So that's the difference between these two. So I'm going to come back to that in a minute. So let's forget about the difference between 1 and 2, and just think about 2, 3, and 4 here. They're all quite different to 5 and 6. Right? In this case, I suddenly have 3 critical points, where before I only had 1, and there I've got 2. So the number of critical points has changed. It's a very clear indicator of a change in the qualitative nature of the set of solutions, right? Okay, here's a slightly more sophisticated way of organizing all those graphs. Same potential. The x-axis here is B, and the y-axis is A. Now let's fit the pictures we were drawing into this diagram. So I hope I don't make you dizzy by flipping backwards and forwards, but so this one here, A equals -8, B equals 0. That's down here, right? Okay, what about this? A equals 0, B equals 0. That's at this, those are just axes. They're not actually mathematically relevant. Like this is a curve that goes up and then comes back down with a cusp here, hence the name. So that point there is the flat bottom basin, x to the 4. And then I guess these dots refer to, I'm not telling you what this curve is yet, I'll tell you in a moment. that one corresponds to that curve over there. It's got a sort of a flat region over there at 2. Right? It's this one here. Okay, so as you move around in this space, the control space, the space of control parameters, this curve Vx is changing and its qualitative nature is changing. And its qualitative nature changes exactly when you move across this curve. And that curve is called the separatrix. Okay, so it's easy to understand what defines the separatrix. The number of critical points, right? The number of critical points is the number of solutions to gradient equals 0. The gradient of V is x³ plus ax plus b. That has at most 3 roots. So there's either 1, 2, or 3. There's 2 generic cases. Those are the open regions in the control space, so the interior of the cusp, sort of region down the bottom, marked 3. And the region sort of on the outside, marked 1. They have respectively 3 critical points and 1 critical point, and then there's this lower dimensional strata, the cusp itself, where there are exactly 2. Obviously, we're in the real case.
Sorry.
Yeah.
Okay. So just for my understanding, so at the very top bottom, I have 3 critical points.
Yep.
That's what's labeled as the 3-phase, I guess.
Yep.
And then to the left and the right, there's 2 different phases that have well, still 3 critical points.
No, only 2.
2. Okay. And then, so is the B, is this like an axis?
Sorry.
Or is this like part of the actual diagram?
On the dot, there's 2. Out here,
Yeah.
there's only 1. This is not a critical point. So there's like a pair of like conjugate imaginary, complex roots.
But everything in the 3-phase has 3 generic points. Is that correct?
They don't all look like that. They look a little bit different. Like one basin will be lower than the other in different parts of that region.
Right. So the points where there's 2 critical points are very thin.
That's right. It's just on the line.
Okay. And whereas the 1 is also very large.
Everything on the outside.
Right. Okay. And is that the little like thing to be? Is that an axis, or is that like
It's
in
just
the
an
phase
axis.
diagram?
Yeah.
Okay. It doesn't mean anything. Okay. Thanks.
Any other questions? Okay, so the degeneracy of the critical point. So if you want to know, so find a critical point, that means you're solving that equal to 0. For it to be a repeated root, some second derivative needs to vanish, which means you're solving this. That only has 2 solutions, right? Threefold, third derivative has to vanish, and that has 1 solution, which is that x equals 0. If you take x equals 0 and substitute it into there, you get a equals 0. Substitute that into here, you get b equals 0, which tells you that the only triple degenerate critical point is at the origin. We also deduce that the 2-fold critical points are on the cusp, because if you take this equation, take 3x squared is equal to minus a, and back substitute, you'll get this equation.
So critical points aren't conserved, like higher up, they're less critical.
The number is not. No.
Right.
Like you could say that when they merge, they become a more degenerate one, but the number is not. That's right. Okay, just to repeat, this region, which is the cusp there, defined by this equation, or by the condition that there's a 2-fold degenerate critical point on that curve, is called the separatrix, or the bifurcation set.
Sorry, to pin you, yeah. You said the number is not conserved, but okay, the sort of, if you count the
even the counting is not conserved,
right?
Because here these have become a pair of, like, these are not real roots anymore. So there's not a repeated root here. There's only 1.
Oh, so the conserved is only if I look in the complex.
Yeah, just don't think about it as
right.
concept.
Okay, so they disappear. Okay.
Okay, so let's put this into a bit more of an abstract framework. So we've got our function v. It depends on two kinds of variables. Note that we sort of actually get to decide which kind of variable is which. I'll come to that at the end. Like if we start with somebody just hands us a potential, like the universe doesn't come with labels saying, this is a control variable, that is a state variable. Okay. So to some extent we get to decide, but there are conditions for that model to be a good one. But we're going to just presume it's given. Well, now the critical manifold, which of course is not a manifold, is given by the set of points where there's a critical point. That is, take all the points in the space of sort of the x-axis in my plots, take all the pairs of a state variable and a control variable where the potential has a critical point at x when the control variables are set to c. Okay, so this is all the critical points across all the different values of the control parameters stuck together in this structure, which, yeah, under some reasonable conditions is a manifold. I'll state the theorem at the very end of the talk, which says under which conditions this is a manifold. So there's a canonical projection, which just sends the pair xc to c. Now, not all critical points are created equal, as we've just discussed, right? We talked about, well, there wasn't a no, I didn't say non-degenerate, I said a critical point, a twofold, a threefold, and of course, depending on the degree of the polynomial, if it is a polynomial v, you can keep going. So there are different kinds of critical points, and they separate this manifold, they put some structure on it, right? So the Morse critical points, or non-degenerate critical points, I think Morse functions came up in Edmund's talk, so a Morse function is a function such that at every point its Hessian is non-degenerate. So locally, it has a expression as a sum of squares in local coordinates with pluses and minuses. So that's a Morse function. A critical point is a Morse critical point if the Hessian is non-degenerate. Right? Well, what's the condition for a critical point to be Morse? It's that the Hessian is non-degenerate, as I said. That's an open condition, right? So there's an open set in the critical manifold consisting of Morse critical points. And the separatrix is the image under this projection of the rest, right? So take a control parameter, and then you look at the graph of v as a function of x. If anywhere in that graph there is a non-degenerate critical point, then that control parameter, sorry, I forget what I said. If I said non-degenerate or degenerate. If anywhere on that graph there is a degenerate critical point, that is one that is not non-degenerate, then it's in the separatrix, right? Because it's in the image of this projection of a non-Morse critical point. Okay, so it's the complement. That's the image of the complement. So it's a stratified set, basically because, as I said, there's different levels of degeneracy of critical points, and the structure of that set is basically the story of how phase transitions can happen and the different kinds of phase transitions viewed from a geometric perspective, and I'll explain what I mean.
For us, kind of T is the KL divergence to the truth.
Correct, yeah. So here's our example, and the critical manifold of our example. So V is the cusp catastrophe. Usually you would refer to x to the 4 as a cusp, or probably more like y squared plus x to the 4 as a cusp singularity. The catastrophe part is referring to the fact you've added in these deformation parameters a and b. So what is the critical manifold? Well, I'm going to take x, a, and b such that the x derivative of v vanishes, which is this constraint. So that's, for a moment, just ignore the fact these are two kinds of variables. I'm just sitting inside R3 and I take the vanishing set of this polynomial, right? X, a, and b, just three variables. And so I might get a two manifold. In fact, it is a two manifold. This doesn't have any singularities itself, as is easy to see. So what are the set of Morse critical points? Well, to be Morse, you need to have the second derivative non-zero. So, and be a critical point. So within that 2 manifold, I'm looking for the complement of the set of solutions of this equation. And that's an open set. And it's the pre-image of these 2 open regions that I was pointing at before, right? Think about them in the surface above. Yeah, what more do I want to say about this diagram? I think these coordinates here is not so important, just in terms of explaining the labels on the diagram. I think it's better to look at the next picture and then explain some things. Any question? Yeah. Okay, so let's stare at this for a minute. Okay, so the plot on the right was the control space, and then at every point of the control space, I'm plotting V as a function of X. And then I'm moving that dot around and the graph is changing. Okay, so this is the control space. What is this surface telling me? Well, this is the manifold of all critical points of our system, right? So if I look at a particular control parameter, pre-image under this projection will be the set of all x's at which this particular function v of x has a critical point. 1, 2, 3, 1, 2, 3, right? Local minima, local maxima, local minima. So what happens, now I want you to imagine moving the control parameter from the interior of this region marked 3 to its boundary where it's marked 2. And think about where in the left-hand diagram that is. So it's over there, right? So moving to the left here means collapsing these 2 critical points to 1. Which is what's happened here, right? So this flat thing here, which is a degenerate critical point, is what it looks like when a local minima and local maxima annihilate. That's just minus x cubed, right? You know what that looks like. Right? Okay, so moving in the control space to the boundary of that region 3 means collapsing those 2 critical points to one another. The other critical point, which is the local minimum on the right-hand side, is just along for the ride. It doesn't care, nothing happens to it. Okay. Moving to the other boundary would be moving off this way, and you would collapse the other 2 critical points, as you can see. And then the bottom one doesn't change. Okay, so that's a picture of deforming this potential x to the 4 by 2 control parameters a and b. And by doing so, having some generic situation with 3 critical points and looking at various different ways of collapsing subsets of those critical points together. And that picture of a Morse function and different ways of collapsing critical points to one another is like a sort of deep geometric story. Okay, what's this got to do with phases and phase transitions? So here we input the kind of first physical information, which is that at a given value of the control parameter, so we're supposing now we've got a physical system that's described by this potential, that's evolving, governed by this potential. And we're going to assume that the state of the physical system is at a local minima of V. Okay, so a stable critical point. One with a non-degenerate Hessian with all eigenvalues positive. Okay, so if we understand all the equilibria, meaning the stable critical points, stable local minima, and the critical values. Okay, so this is the second part. Actually, this came up and I was explaining something, I think, in response to one of your questions in Jesse's talk, and I talked about critical values and critical points, right? And the 2 things can happen. The critical values can cross, in which case you get a first order phase transition, or critical points can somehow merge. And that's what I'm talking about here. Okay, so let's go looking for critical points. Now, here's actually where the standard story in catastrophe theory does not really apply to what we're talking about in SLT. Okay, so I'm going to tell the story from the point of view of what's in the textbook and the usual way you think about it, but this isn't a completely good fit right now. Maybe I'll come back to this a bit later. So just to flag that, in case that seems a bit confusing. Okay, so for a generic family of potentials, for almost all values of the control parameter, the potential will have only isolated non-degenerate critical points. No higher dimensional loci of critical points like we see in Liam's talk, for example, right? So there's an open dense set in the space of functions where that doesn't happen, right? Where every critical point is isolated and non-degenerate. And the assumption that's setting this up is that for almost all control parameters, you're moving through that part of the space of functions, and you only hit sort of things that have degenerate critical points at isolated values of C. Now, the kinds of control parameters we might be interested in may not satisfy that. They may lie in some subset of functions that's kind of generic in a slightly different way. This literal formulation will apply in a situation that I'm going to describe tomorrow. So this like can apply, but there's some open questions here about how we translate exactly our requirements. Okay, so anyway, the isolated non-degenerate critical points, let me label them X superscript 1 through X superscript P and so on. So P is the index that labels the critical points. The equilibrium condition, which says that all the partial derivatives of V have to vanish, the X partial derivatives have to vanish at the critical point, gives you some equations. And those have isolated solutions. So that's, and as you vary C, those isolated solutions also vary, right? So this is like, one of the confusing things when you think about phases is that a phase is not to do with the value of a free energy or any potential at some particular control parameters. That's not a real thing because temperature and pressure are always varying in physics. So you think of the control parameters as not fixed values. There's no such thing. Okay. In the experiments under your control that you're paying attention to with thermodynamics, there's no such thing as fixing the value of C. So if a phase is something that's so sensitive to the value of the control parameter that it only exists at some particular value, it's not a real thing. So a phase sort of has a fuzzy identity where it has to exist for some region of values of C. And that's ultimately, I guess, the inverse function theorem in this case. So you can actually take this critical point, it exists for nearby values of C, although its position might change. And therefore, at least for some region of values of C, think of XP as a function of C. Okay, that's valid. Not for all values of C, that's the whole point, but locally it's true. So these XPs as functions of the control parameters are called equilibrium branches or phases. As a critical points of the potential as a function of the control parameters. As C varies, their positions change, as do the eigenvalues of the Hessian. And that's the kind of identity of the phase. The number of critical points can also change. We've already discussed that. And I've said that. Okay, this is new notation. The critical values are the values of the potential of the critical points, right? The heights of the local minima or maxima, for example. If the critical points are functions of the control parameters, then so too are the critical values. Okay. So in this framework, a phase transition occurs when the point, which describes the state of the system, so remember the system is going to be at a local minima of the potential for any given value of the control parameter, when it jumps from one stable critical branch to another. Stable meaning it's a branch just refers to this family of critical points as a function of C. It's stable if all the eigenvalues are positive, right? So it's always a local minima throughout its entire sort of lifetime. If the state jumps from one stable critical branch to another, and that includes when critical branches meet or disappear. Under the Maxwell convention, there's two kind of conventions in thinking about applying this to physics. One is the delay convention, one is the Maxwell convention. I'm mostly going to be talking, actually I think I'll entirely be talking about the Maxwell convention. So if you want, I can explain at the end what the other one is. The bottom row here is the Maxwell convention, which says that basically it's the framework we've been talking in, which is that, so here you're varying the control parameter in a way that makes the potential change in the direction from left to right. The system is here in the deepest local minima. It's still here because that's deepest, but at some point this goes infinitesimally above that, and at that very instant the system jumps to that other state and then stays there. That's the Maxwell convention.
So if we're thinking of the potential as the KL divergence to the truth, then
yeah, we think you should probably think more of this as a graph of the free energy as a function of some parameter rather than the KL divergence.
oh, right, right.
And so this
right.
is like a phase and then it jumps.
Yeah. So do we feel that the Maxwell convention is like kind of okay? Like because it's the jumps are quite quick, or
In Bayesian.
Yeah, that's right. Like from a Bayesian point of view, the posterior doesn't care if like
Right.
it has to jump to a completely different path.
Right, okay.
SGD, for SGD, it's more like the delay.
right, I see. Okay, thanks. Yeah.
Any other questions? And both have their problems, obviously, right? So under this convention, somehow the state needs to jump almost instantaneously, perhaps quite far with respect to the x-axis. Under this convention, you can have a system persist in a non-global minima for a very long time. Might also, I mean, this basically comes down to the fact that I'm not talking about time in this story, right? And that's a limitation. So in this story, it's basically equilibrium thermodynamics, right? There are equilibria and then you swap equilibrium. There's no story about how that happens. Okay, so that's like a limitation of the framework. And under that limitation, you sort of have these two hacky choices. Okay, it's okay. Usually when we're talking about phase transitions, we have in mind like some single parameter maybe that we're varying, or we're taking well, not a single parameter. We think of a curve in control space, right? So that's going to be C. C is a function of S. S is now like time, if you like. So I have some particular protocol for varying the temperature and pressure in my experiment. And I've got my hands on the dials, and as a function of time, I'm changing both of them, right? That C is a function of S. As you change the control parameter, the critical points move around in the space of X variables, and the values also change. Okay, so I need two notions in order to define phase transitions precisely. The first is the separatrix, which I've already defined, also called the bifurcation set. Notation for that is SB, B for bifurcation. That's the set of all control parameters at which what? No, yeah, this is not stated correctly. There's a set of all control parameters for which has at least one degenerate critical point. That's just completely wrong. It's the complement that I wrote down. Okay, so with apologies, the slide is incorrect. The separatrix is the complement of the set of control parameters where there are no non-degenerate critical points, or said differently, it's a set of control parameters where the potential has at least one degenerate critical point. Okay, there's the cusp thing, the lower dimensional strata where something happened when you cross it. This measure zero set organizes all the qualitative changes that happen together with the Maxwell set. So the Maxwell set is where at least two critical values are equal. So that is, you take, it's a subset of the bifurcation set. Okay. No. Why? Okay, I'm sorry. The Maxwell set is a subset of literally what I wrote there, but that is wrong. Okay. It's a set of, it's a control parameter where, no, maybe I have written it correctly. No, it's not a subset of that. Okay, so it's a control parameter where you only have non-degenerate critical points, so it's a Morse function. But in that Morse function, two of the critical values happen to be equal, right? So you've got a Morse function, it's just a bunch of local minima and maxima, nothing more complicated. That's generic, but it's only generic if all the heights of all the minima and maxima are distinct, right? You're in a lower dimensional strata if two maxima are exactly the same height. That's the Maxwell set.
So that's about the critical value.
That's right. So that's where two critical values hit, right? The separatrix is where two critical points hit. This is where critical values hit. Maybe more than two, right? Maybe three merge together at once in the Maxwell set. Maybe three merge together in three critical points merge together in the separatrix. Okay, so this was a bad but with that understood, a phase transition induced by the variation C is when the curve crosses either the bifurcation set, so two critical values collapse into one another, or the reverse, or you cross the Maxwell set. So this is critical points, this is critical values. Okay, so let's come back to this diagram here. We already talked about this as the separatrix, so any path that goes across that will be associated with a phase transition. But there's also the Maxwell set, which I'll now explain. So let's consider three curves marked here as 0, 1, and 2. The separatrix is, as I wrote there, the Maxwell set is the set of B equals 0, the set B equals 0, A less than 0. I actually remarked on this earlier, right? So in this bottom region 3, you have something that looks like whatever that is, a thing with two minima. But generally in the region 3, one of the minima is lower than the other, right? The line where they're exactly the same height is right in the middle. That's the Maxwell set. That's the picture I drew was on the Maxwell set. Okay, so I claim that on curve 1, there's a first order phase transition as you cross the Maxwell set. On curve 2, going down, there's a second order phase transition as you cross this cusp point. I haven't defined first and second order transitions yet. On curve 0, there is no phase transition under the Maxwell convention. I mean, over here, there isn't any. Yeah, this is a bit of a misleading statement. I mean, the infinitesimal part of, the piece of this curve that crosses here is not a phase transition. Okay, this part is for the same reason that 1 is. Okay, so let's talk through curve 1. So it's marked in green over there. So if I start a little bit to the left of the pink dot, it looks like this. So I'm moving along the green arrow. Sorry, I need something to point with. Okay, if I take the green line at its very beginning, so outside in this region 1, it looks like this. There's only one critical point. That's not a critical point. It's just like something of a slightly different slope. So the very beginning of the arrow, there's one critical point. The state of the system is in it. Now I'm going to move along that green line. Now I'm inside the region 3. In between here, there was actually something happened because that became a critical point. And then, so in between here and here, this is nothing right now. It's not a critical point, but at that region, a critical point was born. It was a degenerate critical point, and then it split into two, a local maxima and local minima. That isn't a phase transition because the system doesn't care, right? It's down here.
In the Maxwell convention.
In the Maxwell convention, correct, yeah. So in the delay convention, that could have been, if it was the lowest thing, could have, well, in the delay convention, that could have been a phase transition if the system were there. Okay, so here we're getting close to the pink point from the left. This local minima is moving down. It's about to be equal, and it's equal, well, in between these two. So right here somewhere is actually where the pink dot should be. So that's where they're exactly the same height. That's on the Maxwell set. And then it moves off to the right. That other local minimum moves up and it's about to die. Well, it doesn't actually die in my diagram. Okay, is that clear? Yeah. So this is a second order phase transition. This is starting at the very top of the arrow, out in the region 1, away from the cusp, away from the separatrix. It's just something that looks like a parabola. This is A greater than 0. A is decreasing. At 0, we get the flat bottom basin x to the 4. And at A less than 0, we're on the Maxwell set, but down in the region 3, we have 2 local minima and 1 local maximum. Okay, so those are 2 paths in the space of control parameters which pass through either the Maxwell set or the bifurcation set, the separatrix, or both. Right? Okay, so when we say first and second order, that's because of the following definition, which hasn't appeared so far this week, so we should at least state it. These days, you probably wouldn't be that confident about saying that, you know, all the phase transitions in nature are 0th, first or second order, because we know many more phase transitions than we knew at the time this book was written in the 80s. But this is like, well, it's like learning about Newtonian physics or something first, right? Like you'll see people refer to the Ehrenfest classification because for many of the phase transitions you encounter, it's a useful characterization. Okay, and this is what it says. It says that if a phase transition occurs because the system state jumps from the pth critical branch to the qth at C S0, as S increases through S0, the transition is of order M if, well, as you jump from the pth branch, so you're running along with critical point P, and there's some value of that, the critical value, right? It's changing as the control parameter changes, but that's a smooth thing that's happening. Now, when you jump to another critical branch, well, the critical value could change, or the critical value could stay the same, but the change could be not continuous with respect to the change in the control parameter, or the value could be the same and the derivatives could be continuous across that phase transition, but the second derivatives might not be continuous. And so that's what makes it order M. Right, so if the highest order to which the derivatives agree across the phase transition, which is, this is before and that's after, so epsilon goes to 0 means just before the phase transition, epsilon goes to 0 over there means just after when you're in the qth branch. Okay, so for a first order phase transition, the critical value is continuous, but the derivative isn't, and second order is the critical value and its first derivative are continuous, but not the second. I won't go through the calculation. If you go back to the previous slide and sit down for 5 minutes, you'll convince yourself that indeed those paths are first and second order respectively. It's not difficult. All right. Now, why do I say this is about thermodynamics? I've used the word phase, I've used the word phase transition, but just because I use the words doesn't make it true. Like, why is this something to do with thermodynamics? Well, so you can formulate the usual setup you'd give in a thermodynamics textbook in this language using the critical manifold and so on. And then you'll see, for example, that the phase diagram we were looking at yesterday, I think, with solid, gas, liquid, triple point, critical point, pressure on the y-axis, temperature on the x-axis. Well, let's just play the game of not knowing these two things are related. Okay, so physicist comes up with the left-hand thing, laborious experiments, coexistence curves, 5 years of hard work. Wow, that was difficult. Mathematician, 20 minutes, a piece of paper. AQ, I mean, x to the 4. What can I say about x to the 4? Okay, beautiful separatrix. It's first and second order things, phase transitions say. Why I claim those things are related? What's the reason? Well, the critical point is the reason that they are related. This is actually an extremely deep observation. It comes back to the question Stan asked yesterday, I think, about like, okay, if the critical point is actually this, like, this one point in the phase portrait, why somehow is it so important? Okay, so somehow there's this very special point over in the control space for the cusp catastrophe. And if you think through this story about first and second order phase transitions that I've been telling, and if you just look at the plots that I don't have them with me. Oh, this one. Well, this of course looks a lot like the curves that we were drawing for the free energy Jesse's talk, right? And the paths we were drawing through the phase space for the fluid exactly had these two phases changing place and the other kind of interactions they were having. There was like 3 local minima, right, for these 3 phases, and sometimes they were coexisting and sometimes not. Okay, so there's it looks a bit like the curves we were drawing earlier. That's not the only reason to connect these things, and then you can sit down and actually derive. I don't actually know a completely convincing story about this. Gilmore's story is like, yeah, fine for this talk where I'm not actually going to do it, but I think it's maybe a little hand-wavy in some places. But what you can do is try and match up. You can say to yourself, okay, if I suppose that this critical point is the same as the cusp point over there, how do I match up these pictures? Well, I'd have to somehow match up the control parameters for the cusp catastrophe with temperature and pressure. I can suppose that relationship is linear and invertible. And you want to match up this coexistence curve with the Maxwell set, because they're the same thing, right? The coexistence curve is the liquid phase and the gas phase having the same free energy. That's the only way those two phases can coexist, right? So they have to have the same free energy. So you're on like the Maxwell set. The liquid would be the low volume phase, and this would be the high volume phase. And that sort of motivates the identification of X, which is the sort of lower axis in our pictures of the potential, with 1 over the volume. Okay. So if you take X to be 1 on V, and you sort of try and match up A and B, it sort of works, and you can derive the van der Waals equation from the equation for the cusp. So that's kind of pretty satisfying. So in some sense, these are the same picture, with the critical point identified with the most degenerate singularity over there. Okay, that's cute. Why is that so interesting? Well, this illustrates exactly the point that was being made by Jesse earlier, which is about many different systems actually having the same description at criticality. Right? Like, so over here, I haven't thought about it, but I don't see any reason to really think that the description of this physical system is related to this, although maybe it is. So I'm not making that statement, right? I'm making a local statement that near this critical point, this system is sort of isomorphic to that one. That happens at critical points because somehow because of the scaling behavior at the critical point. There's only so many ways you can scale. That's a very loose way of talking about classification theorems in like critical phenomena, but so there are formal theorems that say more or less something like that. So at this critical point, these two systems are isomorphic, which lets us use this simplified model to describe what's going on over there. And that's a statement about universality. And the reason why this A3 singularity shows up all over the place, because it is like the Platonic mathematical avatar of this universality class. Yeah.
Is there a physical interpretation of these curved lines as well?
Yes, there is. I probably can't give a good story of it, so I'll have to look in Gilmore's book and explain it later. But yeah, there is. Yeah, if you think about what it looks, it's sort of where the other two phases somehow merge, right? So there's some part over here where maybe solid and liquid stop being different. So yeah, a bit fuzzy on what it is, but yeah, it does have an interpretation. Okay, so just to remind you, the critical manifold, the projection chi, and the separatrix. Yeah, looked at that. Okay, so here's the real math, right? So I've just been giving you definitions. Why should you believe that any of this is ever tractable in practice, right? Like, okay, yeah, I've got some potential, but then I go look at its critical points. Crazy object, I'm over, done, right? There's no theory there. Why should you believe? I mean, I'm claiming that this is one of the ways in which geometry enters into the description of physical systems, dynamical systems. And basically the statement is that this story with x to the 4, the cusp, the A3 singularity, and its unfolding, this control parameter space, is not some exotic special case on the very corner of the space of physical systems. This is really quite typical. From a mathematical point of view, the reason it's typical is Thom's theorem, which says something about transversality and sort of generic points in the space of functions. But it cashes out to the following statement. So maybe I'll go through this table first. So we were looking at A3, right? It's x to the 4. That's the granddaddy of the whole unfolding. It's the most complicated thing, which when you pull it apart in different ways gives rise to all the other points. The way you pull it apart is by varying a linear term or a quadratic term. So there's two control parameters. They were A and B before. 2 is the number of control parameters, and forget the -3. Okay, so that's one of them. That's one of the catastrophes, but there's all these other ones. Okay, so A2, A4, and so on, for D and E. These are labeled for A, D, and E, right, in the ADE classification. So this is where Timaeus comes back. Okay, so those are families of singularities and ways to deform them, to get simpler things. Right, when you deform it, you never get a more complicated thing starting from this, right? You get simpler things. Okay, so Thom's theorem, kind of fairly loosely stated, says that if the number of control parameters is less than or equal to 5, then generically, that is, there's an open dense set in the space of smooth maps. I won't tell you right now what the topology on the space of smooth maps is, but if you know anything about this kind of thing, it's the usual topology. So there's an open dense set in that space. So generically, if you take your potential to be F, one of these generic potentials, which I kind of talked about earlier, then MF is in fact a manifold of the same dimension as the space of control parameters. So we were talking about A3, right? So the manifold of critical points was 2-dimensional. And it's defined by one equation, right? That says gradient equals 0. Sorry, that's K equations, right? For the number of control parameters. So, sorry, it's N equations. So I drop the dimension from an MF sits inside Rn plus K. I drop it by N dimensions for the N different state variables. Okay, so generically, that's a manifold. The only singularities that you encounter are elementary catastrophes. That is, they're on this list. So singularity of the map, chi F, is a map between two manifolds of the same dimension, two-dimensional, right? And it maps to the space of control parameters, which the first property here says is k-dimensional. A smooth map between manifolds of the same dimension is has a singularity at a point of the Jacobian that's not invertible at that point. Question? Yeah.
You just clarify what K.
K is the number of control parameters. So in our case, it was 2 with the cusp. But here it would be, right, there's 5. This is a more complex singularity, so there's more ways to kind of pull it apart. Okay, so any singularity of chi-f, that is a point where the map chi-f doesn't look like just a change of coordinates. For example, here, or there, or in fact on that whole line, right? So the set of singularities of the map, chi v in this case, are precisely the points that lie above the separatrix. And what the second part here says that if you look along the separatrix, you only see elementary catastrophes. Well, of course, we know that's true here because that's an x to the 4, right? But it's also true as you cross this boundary that what you're doing is one critical point sits off on its own and the other 2 somehow merge. That's an A2 catastrophe, the simpler one down the hierarchy. So the only stuff that happens at the points where chi-f is singular are the stories that are on this list, that are implicit on this list as you look at paths through the control space. So this is a complete description of what happens at the separatrix, as long as the number of control parameters is less than or equal to 5. And this doesn't really matter for our story right now. Okay, so the upshot of this is that if your number of control parameters is less than or equal to 5, catastrophe theory sort of tells you what happens. Right? And it's governed by these singularities and the deformations that are in the unfolding of those singularities. So this is the sense in which ADE governs many thermodynamic systems of low number of control parameters. Okay, I think I just have one more slide. Are there any more questions about this one? Yeah.
What do AD and E mean, and why is the subscript off by 1 from K?
Good, yeah. So AD and E, the letters don't mean anything as far as I'm aware. ADE classifications, there's many of them in mathematics. So you know what AD and E stand for?
No, well, no, but I was wondering that these would be groups.
Yeah, that's right. Yeah, but that doesn't explain what the letters mean. Yeah. Well,
Ultimately,
dihedral exceptional. Yeah, that's right. But like, okay. The E. Okay, so there are many things that are classified by ADE. So there's groups, finite subgroups of SL2. There are quivers. You could go on for a whole hour about things classified by this scheme. Yeah. So this is a very common pattern, and this is one of them. So the classification, we don't see all the E singularities here, right? Like E7, E8 are missing. There's nothing above D6, and this is only the beginning of the A series. So this is not all ADE singularities. Yeah.
So there's a question.
Oh, sorry. There was a second part to your question, wasn't there? Did I answer?
Oh, about the subscripts be off by 1 from K.
Oh, yeah.
I guess that's probably just compound convention groups.
Yeah, there's a reason for that, but yeah, it's meant to be off by 1.
Okay, so just to confirm, so these names on the left are groups. So they
say they're groups. They're just letters, and they happen to also classify some groups, but the group classification has no like primary status relative to the other.
So there's not a group action lurking
Oh,
here
there is
somewhere.
Yeah, that's right. I mean, you can think of this as the invariant polynomial if you act on this group on C2, and then you look at the coordinate ring, the invariant polynomials spanned by 3 invariant polynomials modulo this relation.
Okay, but the relation is kind of complicated. It's not directly in the.
Well, it's not true, but yeah.
Right. Okay. What happens if I do K6? What happens? K, the number of control parameters. Is it just arbitrary that he stopped at 5? Is it becomes intractable for 6?
I do not understand the details of the proof of the theorem, so I can't answer this question. I don't know what happens at 6.
Right. Okay. Bad thing.
Well, I don't know. Yeah.
There was a question slash comment from the chat, which is about the notion, introducing the notion of time.
Yeah.
Which is more or less introducing the idea of transition rates and also sort of activation energy if you want to jump from higher and jump over a hump and things like that. And so the question is
maybe I can ask myself.
whether or not that is a correct notion, and he knows these things from nucleation in the easing model. Yeah. So.
Yeah, I don't think I have anything kind of deep to say about that. I mean, it's pretty straightforward to start putting time back into this picture, like transition rates, for example. Gilmore's book will show you how to do that. But obviously, if you have a system sitting at a critical point where it's at a critical point that becomes degenerate and then disappears, right? Then that's a pretty complicated thing to describe, I think.
So I guess in general, here we are talking about kind of like one particle, and in general, we talk about system with lots and lots of particles, and it's kind of like in a vicinity of the system.
I mean, basically all I'm saying is about phase transitions, which are governed by like transitions between equilibria. There's lots of landscape beyond that, about which I don't have anything particular to say.
Yep, thank you.
Okay, so some final remarks. We actually saw the Maxwell set in SLT high 1 because I solved an equation where I said free energy of something equals free energy of something else, right? And then I derived some equations. So that's solving for the Maxwell set. Solving for the Maxwell set is called the Clausius-Clapeyron relations. So if you want a fancy name for that very elementary technique, that's what it's called. If you read the Wikipedia article, you probably won't understand that it is that. Yeah, it looks very complicated. Okay, given a real system, how do we decide what are state variables and what are controls? Yeah, this is like one of the more tricky points in applying catastrophe theory, right? Because first of all, you sort of only have very strong knowledge of the number of control variables is small. What counts as a control variable? And the universe doesn't label them as state or control variables. Maybe it's a control variable because you literally control it. That would be sensible. But more generally, the theory kind of works and gives a reasonable model, provided on the relevant time scale that you're looking at the dynamics. It is the case that as the control variables are changed or change, maybe they're not directly under your control, as they change, they kind of move in such a way that relative to their change, the change in the state variables is fast enough that the state variables find an equilibrium, so that you can actually think of the system effectively as control variables change along some path in control space, and for every value of the control parameters, the state variables are dictated by solving that equation that says the gradient of V is 0.
It's like an equilibrium condition.
Yeah, so as long as that holds, that division of state and control variables is reasonable. Yeah, I mean, in geometry land, you wouldn't say control space, you would say unfolding or universal unfolding or miniversal unfolding. And the control parameters would be called deformation parameters. But under these names, these objects are also very important in singularity theory. Okay, that's it. Thank you. Questions?
Somebody should go first.
Yeah.
So if I'm understanding correctly, is it true that the first order phase transitions always happen on the Maxwell set and second order phase transitions only happen on the separatrix?
Certainly true about first order phase transitions, the second order phase transitions.
there's no other reason they become the same, or because it's a person.
I mean, I don't see why I couldn't cross the Maxwell set maybe in some I mean,
Yeah, sure. I guess it would make sense. Second order could happen on either one of them.
yeah, I think so. I'd have to think about it. But the picture we're looking at is quite simple. So in higher dimensions, the separatrix and the Maxwell set like a very complicated things. Yeah, a good question.
Could you speak a little bit more about what makes the cusp catastrophe such a sort of deeply natural phenomena?
A2 is too simple to be interesting. A3 is the simplest other thing. Well, it's a little facetious, but that is the actual reason. A2 is just the story of, right, so that's rather than varying x to the 4, you're varying x cubed. So you have x cubed, and then as you vary some parameter, it gets a local maximum and a local minimum. No phase transitions, right? There's 2 critical points, but one of them's a local maximum. Boring, right? There's no physics there. The first thing with 2 competing phases is the cusp. And that's often the story we're telling, right? It's not that often that we're concerned with 3 phases meeting and turning into one another, right? Most of the time, phase transitions, we're talking about 2 phases and they exchange place, or they exchange, or 2 critical points merge. And there's a reason for that. It's like part of the theory will tell you that that's what's happening. Right?
And so that probably answers my next question, which is like how to think about how this lecture applies to much higher dimensional spaces and stuff.
Right.
Is just that you're trying to isolate just looking at like 2 particular phases at any time.
So I mean, it's okay, it's kind of like a very weak dimensional answer, but to have a higher catastrophe, you need more complicated things to be happening, right? So there's like, that's less generic. So the most generic way that 2 phases can compete is the cusp catastrophe. So it's completely not a surprise that we go out and look at substances, fluids in the world, and that does match with the A3 catastrophe. 2 phases competing, that's the story you expect. Now, that doesn't mean you're not guaranteed you look at a complicated system and it's governed by cusp catastrophes or something easy with 5 or less control parameters, but it does happen a lot. And so you kind of aren't surprised if you go looking at something that involves a second order phase transition and it turns out there's a cusp catastrophe there. And in fact, you use that the other way around, right? You find some interesting phase transition and you think to yourself, well, if I reparameterize in some clever way, I must be able to find a cusp in here. And if you fail, then you think, whoa, this is a very complicated transition.
So extending the table is really about extending like the complexity of the singularity structure changing.
Yeah, I mean, those things can occur, but if you look, for example, at the papers I was showing in my first lecture with the magic angle, twisted bilayer graphene or whatever, they're not like getting to the end of the table and being like, oh, like these are really boring singularities. No, they're like, they're still on that table. So it's, I mean, it's not to say those are the only things that can happen, but those do happen a lot.
Yeah.
So do you expect the phase transitions that happen in large deep learning systems to mostly be on the table?
That would be the natural thing to guess. Yeah.
Right. Okay.
And the one I'll talk about tomorrow is. So
suppose that's the case. What does this actually tell us then? Like, yeah, we'll have like a little phase diagram.
Well, it tells you that all those transitions can be viewed as moving around in the geometry of those unfoldings.
I had a question about this stratification of the unfolding. Could you say more about this structure on the deformation?
Yeah, the stratification in this case just means the strata are 0-dimensional and 1-dimensional. So the 0-dimensional strata is the most degenerate point, and the 1 strata are just the lines of. So that's, I mean, the stratification is by the order of sort of degeneracy.
Right. Okay. Okay.
So then if you have a A5, you'll have 0, 1, and 2. And
Okay.
that's the swallowtail. It's like some
Yeah.
very interesting topology.
And you said something about these deformation parameters. They're studied in algebraic geometry.
Yeah, sure. I mean, if you study singularities, then you study these deformations.
Right. Okay.
Royal, Shuston, and Lawson is my recommendation for a text on singularity theory, if anybody wants to dig into that.
That's Matt has a request to
Yep.
show a interactive visualization of a phase plot by sharing screen. Is that okay?
Oh, go ahead. Yeah.
Yeah, I think you
I
have to stop sharing.
sharing. Yeah.
I think he will have permission. Go ahead, Matt.
Ooh.
Wait, let me
Can
see
you
if
see
I
my
can get
screen?
it up on the big screen for the rest of the. Hold on, Matt. Don't start the
Yeah,
show.
no problem.
Yeah.
Am I audible?
Yep.
Okay, go
Great.
ahead.
Yeah,
You're
okay.
not audible to everyone else. Can you switch on your audio?
It's gonna
How
be
about
some-
now?
Yep.
Yeah, okay. So, I mean, I kind of got distracted when Dan said at the start, you have to imagine at every point in the space, there's that's the control parameters. There's then another plot that you have to look at. And I didn't 100% follow the rest of the talk, but I made this. So you can move around the point and it changes the potential function.
Oh, nice.
And yeah, you see that when you, well, one thing that was interesting to me was that this one critical point region is kind of connected, and you kind of watch the minimum like move around the origin. And I thought that was pretty cool. But anyway, the phase transitions are the interesting ones, and that's, or when the critical points, when the critical points of the potential changes. And yeah, this is the line that Dan pointed out the equation for, so I put that on the plot, and you can see that's where the saddle point appears, and then it turns into another local minimum, and then you've got the 2 local minima down there. And this is the point where they both disappear, and it turns into a quartic critical point for a second. Yeah, so
Thanks.
that's what this is the notes that I took during the talk, I guess. Unfortunately, I was thinking, how could I visualize it'd be really great to visualize that manifold that's floating above the space, but that's way above my skill level with this stuff. So that's all I got.
Thanks, Matt. I will resist the temptation. You had a question, Jesse?
Yeah, I guess 2.
Yeah.
So first of all, this distinction between state and control.
Yeah.
I mean, we have physical systems. I guess turbulence might be an example where this gets messed up. Where
Oh, I see, where it doesn't actually settle to a critical point.
or where
Yeah,
the
yeah, yeah.
time scale separation is not clean.
Yeah, for sure.
What would that mean for neural network?
Yeah, I don't know. Give me a PhD student in 3 years and then I'll answer.
And then another question. In quantum physics, energy levels are quantized because we're really moving among different Riemann sheets, right? So you move in the complex plane, you circle around.
In the quantum case, phase transitions are dealt with differently. You have degenerate energy levels. So this the set of states is.
Is it the same picture?
Yeah, but it's the same picture, but so a quantum phase transition is defined to be where the ground state energy, which is a function of the control parameters, changes, right? And like exchanges with some other energy level. So you'd have energy levels meeting or changing places. Yeah. And then those would be perhaps described by different symmetries. So that would be, it's a similar story, actually. It's in Gilmore as well. But you set it up differently. I mean, it's conceptually similar, but sort of different mathematical ingredients. Yeah.
Could you speak a bit more about taking the contents of this talk into the deep learning setting or the SLT setting? And is it mainly a conceptual framework that we should be thinking about? Is it something to do with the connection to algebraic geometry? And like, do you expect that there's interesting insights there?
I feel like a relentless huckster for selling the talk tomorrow over and over, but this will explain it in that context. It's actually not completely straightforward, which is, I mean, okay, you look at all this and then you're like, okay, but we were talking about phase transitions in N, right? There's only one. It's not even a continuous parameter. I mean, you can think of it as continuous, it's fine, but that's only one parameter, right? Like, okay, so where's the control space if we're just varying things in N? But that's not what I want you to think about. I also don't want you to think about N and some other thing. That isn't the way this maps into the situation. The way you should think about this is a local story that's to do with criticality, right? So it may be the case that there's structures in the loss landscape that look like the kind of singularities that are present here. And as the Bayesian posterior sort of interacts with them, or SGD passes through them or interacts with them, the dynamics might end up sort of for criticality reasons being well described by one of these catastrophes. So it's like adjoint to, but not identical to the story of phase transitions we've been talking about, right? So this is not meant to be like meshed with the story about phase transitions in N. I mean, that's a fine way of thinking about this, is giving you some mathematical insight to that story as well. But the way this actually gets realized in describing like what's happening over the course of training is more subtle than that. So hopefully after tomorrow, it'll be sort of clear what I have in mind.
Matt has a possibly similar question. So the state parameters seems to be the model parameters, and he's kind of asking whether the control parameter would be the data space, so X.
Yeah, so I mean, if you had, you could think about, like in the context of Liam's talk, some sort of hyperparameter in the truth and some other hyperparameter, and having a control space like that. That's perfectly reasonable, yeah. So that would be a situation in which this, you might expect to see. So anytime you have two control parameters and you see some kind of transition, very, very likely you found a cusp catastrophe.
Yeah.
Right. So if you're varying, if you're varying a parameter in the truth, or maybe in the prior and some other parameter, then you suspect maybe something like this is involved. That in the context of tomorrow's talk, they'll all be model parameters. So like you do get to choose, and there will be many ways. I mean, that's what universality kind of means, right? Like if you have a thermodynamic system and phases and phase transitions, there will be many angles from which you can map this kind of abstract story onto what's happening. It's not like there's not one true way of seeing the phase transitions. So it's not that there will always be that some of the control parameters are like, they might be model parameters, they might be something else.
Okay, I'm just going to read Matt's response. Okay, so control parameters would not be like every component of every data vector. That's what I was thinking. So because he was thinking about like the data vectors instead of Q.
That's probably greater than 5.
Yeah.
You can try that, Matt.
And he's saying, but rather it's some more abstract true parameters from which the data is generated. So yeah, the meta hyper parameters.
Yeah, I haven't thought about that. So Just guessing you might find cusps there, but yeah, that's what you'd expect.
The one in Liam's presentation is explicitly hyperparameter in the true
Yeah,
distribution.
is there a cusp in your talk? I
Sorry.
don't know.
Oops. Okay.
Any more
Any more
questions? Seems we're finished here. Okay, thanks
Thank you,
everybody.
Dan.